Whether you're taking Calculus 1 or Calculus 2, trigonometric integrals are essential to your class. A lot of the times in Calculus 1, you're simply given the general form of these integrals, but in Calculus 2 class, you examine these in a deeper form. These integrals are fascinating because they show up in many different areas of mathematics, and there's actually a very beautiful way to relate them to the right triangles. And in this video, we're going to cover 3 essential integrals and triangles that we need to know whenever we're encountering these types of problems. You ready? Let's get started. So here's the first integral that we're going to encounter. We have the integral of 1 over the square root of some constant a squared minus u squared with respect to u. And there's always a deep connection to the right triangle, so every single time we have a problem like this, I suggest to write out this right triangle with your theta right at the bottom. Now, whenever you're encountering the constant squared minus the variable squared, you want to go to your triangle and make the opposite side your variable, and you want to make the hypotenuse side your constant. And notice that I make them u and a. That's going to be very important because if you were to use Pythagorean theorem, you will find that this adjacent side is the square root of a squared minus u squared. I'll actually show it the first example, and in every other integral, I'll just write it down every single time. But really what you're doing is you have, let's just say, for example, this is your b. Then you have b squared plus u squared equals to a squared. And if you were to subtract this to the other side, you get b squared is equal to a squared minus u squared. You take the square root and you get that b, which is your adjacent side, is root a squared minus u squared. And that's how we get that there. And now we're going to go ahead and set this up. So again, we have the square root of the constant minus the variable. This is where you have to set up, looking at your right triangle, you're going to make sine theta, and we're going to use SOHCAHTOA, is equal to your opposite over your hypotenuse. So u over a. And now you can go ahead and move the a to the other side, and we have a sine theta. This is what a lot of people always, or a lot of teachers always tell you that you should have memorized, and this is exactly where it comes from. And it's essential to know the right triangle because it shows up many times whenever you're solving integrals like this. As we continue, we have our sine theta is equal to u over a. Let's go ahead and find our differential. So we're going to take the derivative of this, giving us cosine theta d theta is equal to, well, there's an a right here, my bad. I took the derivative of this. So it's going to be a cosine theta d theta is equal to our du. And this is essential because this is our differential du. And as you can see, we need that for right here. One other thing that we need now is we need a representation for this square root value. Well, we have it right here in the adjacent side. So we're going to use the adjacent side. And since that has a variable, we're going to use a side that doesn't have a variable, which in this case is a hypotenuse. What's the relationship between the adjacent and the hypotenuse? Well, that's cosine. So we'll say that cosine theta is equal to the adjacent, a squared minus u squared, over the hypotenuse, which is a. So we can go ahead and multiply the a to the other side and get that a cosine theta is equal to root a squared minus u squared. And so now we have a nice relationship for the square root of a squared minus u squared. Let's go back and revisit our integral. Now we're going to go ahead and start rewriting it. We have 1 over this entire value on the bottom. Well, that's this right here. That's a cosine theta times our differential du, and that differential du is right here. We have a cosine theta d theta. And look at this. Now we have a nice integral that has nothing but thetas, no u's whatsoever. The a's we don't really worry about because they're constants, but in this case, notice that the a cosine theta cancels out with the a cosine theta. So we're really just left with the integral of 1 d theta. Okay, a simple integral of 1 d theta is going to yield theta plus your cheese, or your constant, if you want to think about it that way. Okay, we officially found the answer, but in this particular case, we want our solution to be in terms of u because that's how we started. So we go back and revisit this section right here. Okay, we have sine theta is equal to u over a. Well, what happens if we take the arc sine of both sides? We would get theta on the left because we took the arc sine, and we would get arc sine of u over a, and that's exactly what theta is equal to. So let's go back to our integral over here, or the solution that we found, and we're going to get that instead of theta is sine inverse of u over a plus your cheese, and that is the first solution. A lot of the times it's not that easy. Sometimes you have to deal with other values. You might not have just theta, you might have cosine, you might have sine, you might have tangent, and in that particular case, it's important to have this beautiful right triangle because we can always revisit it and find whatever tangent is or cosine of that may be. I'll make a later video on that to show you the more intricate integrals that can come up with problems like this. So now let's talk about probably the most popular integral out of the three. This is something that a lot of people recognize right away as the arctangent integral. But let's go ahead and solve it and see why that's going to be the case. Once again, I know that I'm going to be dealing with trig functions because I have the constant squared plus u squared. So I'm just going to go ahead and do my right triangle right there. And by the way, you can totally try to do this using partial fraction composition. It'll be a little more complicated, but I think that'll be a good challenge for you. Okay, let's continue. We have the constant squared plus the variable squared. In this particular case, what you want to do is you want to make your opposite side your variable, kind of like what we did with the previous problem. But instead of making the adjacent or the hypotenuse side your constant, you're actually going to make that your adjacent side. So this is going to be u right here, or a. I'm so sorry about that. And again, if you ever forget why that's the case, try to use Pythagorean theorem, and you're going to see that this will become root a squared plus u squared. And again, a squared plus u squared, we have it right there. So it's helpful. And if you were to kind of mess it up, you will notice that you didn't find anything that has a squared plus u squared. Now, I've done this so many different times, and that's how I have it memorized, that we have this. The reason why we're doing this is because I have u and a. These are like the main ones that I want to focus on first. So that's going to be tangent because tan theta is equal to the opposite over adjacent, opposite over adjacent. If I were to move the a to the other side, I have a tan theta is equal to u. And again, this is exactly what I need. Now we go ahead and take the derivative so we can find our differential. Well, we have a secant squared theta d theta is equal to du. And this is going to be perfect. Why? Because we need that for the du right there. Now we need to find an expression that represents a squared plus u squared. Well, we have it right here in the hypotenuse, right? Now that since that one has a variable, we're going to use one of the sides that does not have a variable, and that is this one right here. That's the opposite side. So which one has opposite and hypotenuse? Well, definitely cosine, but in this particular case, and for no other reason than just doing this multiple times, I know that I have to do secant theta is equal to the hypotenuse, which is root a squared plus u squared, over the adjacent a. Now, the reason why I did this is because if you use cosine, then you will have this value in the denominator, and you kind of want it on the top already. So that's why we use secant. But if you were to use cosine by accident, you can just sort of flip it. We can multiply the a to the other side. So a secant theta is equal to root a squared plus u squared. And this is great, but this one doesn't have a square root. If it did, then we would use a secant theta. Now that it doesn't, we're going to go ahead and square both sides and get that a squared secant squared theta is equal to a squared plus u squared. And that's what we need. Look at that. We have it just right here. So now that we have the particular values and we have the du, let's go ahead and find our new integral. So we have the integral of 1 over this entire value, which is this. So we have a squared secant squared theta times our differential du, which is a secant squared theta d theta. Okay. Let's see what cancels out. Well, I see a secant squared, boom, goes away. In this particular case, one of the a's cancels out on the top, but one of the a's on the bottom cancels out only. So you're really just left with an a on the bottom. So what you have is you have integral of 1 over a d theta. Now that's okay because 1 over a is just a constant. Well, we have 1 over a theta plus your cheese. This is awesome because now we found the integral in terms of theta. Let's go ahead and find it in terms of u because that's what the original integral was. Well, we have it up here. We have tan theta is equal to u over a. What would happen if we take the inverse of both sides? Well, we will get theta is equal to tan inverse, or arctan if you want to think about it like that, of u over a. So now we found the theta. Let's go ahead and plug it back in here, and we have 1 over a tan inverse of u over a plus your cheese. And then again, this is the famous integral that a lot of people recognize and they know exactly what the answer is whenever they see something like that. Okay, so now we have the last integral, 1 over u square root of u squared minus a squared. Now, before we continue, I just want to say to please, if you haven't done so, subscribe to my YouTube channel. We are trying to grow to 10K. We are almost there. You know, I try to put a lot of videos on Instagram and TikTok, but I think the YouTube channel needs a lot of love. So please subscribe if you get the chance. Now, let's go ahead and finish this off. We have 1 over u square root of u squared minus a squared. This looks very, very similar to the very first one. Instead though, it's the variable squared minus the constant squared. If you were to kind of go back, you will notice that we did a squared minus u squared for the very first one. So this is the variable squared minus the constant squared. So once again, we're gonna go ahead and draw our beautiful right triangle. We have a right triangle here and we always have the theta there at the bottom. And because you have the constant, or I'm sorry, you have the variable minus the constant. This is going to be very interesting. You're actually going to have u as your hypotenuse and you're going to have a as your adjacent. Now, if you were to do Pythagorean theorem, you will see that the opposite is going to be this right here. Now, again, this one's a little tricky and this is one that you kind of have to just continue practicing. But whenever you have the variable minus the constant squared, it's the hypotenuse is the variable side and the adjacent is the constant side. So let's go ahead and set this up. Well, we want a u and a, so we want a relationship with that. And we're going to use secant. Again, if you were to use cosine, that's perfectly fine, but we want the variable on top because if you have hypotenuse over the adjacent, we can move the a to the other side and have a nice a secant theta is equal to u. Now, we're definitely going to use this because I see it right up there. This is one of the first times where you actually have something a little extra just because you want a nice variable. If it wasn't, it will become a little tricky. And again, that's maybe something I can talk in a later video. Let me know in the comments if you will like that. So we have a secant theta is equal to u. Let's go ahead and find our differential. Well, we're going to take the derivative of this, giving us a secant theta tan theta d theta is equal to our du. This is perfect. Why? Because we need this for our differential up here. We're almost there. Now we just need a relationship for this square root value. Well, I have it here. I have the opposite. So I'm going to use the side that doesn't have a variable, which in this case is the adjacent. Opposite, adjacent, I'm thinking tangent. So tangent is equal to the opposite, u squared minus a squared. Whoops, let's go ahead and make that a little better. Over the adjacent a. Let's multiply that to the other side. A tan theta is equal to the square root of u squared minus a squared. And that's exactly what we need. Look at that. We have that up here. So now let's go ahead and start rewriting our integral. So what we have is we have the integral of 1 over u. So u is a secant theta. So we have a secant theta times this right here, the square root term, which is a tan theta, and then times our differential du, which is this right here, a secant theta tan theta, a secant theta tan theta d theta. Okay, looking at this, and I'm hoping that it wasn't too small. I see that it kind of was. I maybe should have written it a little bigger, but that's okay. You're gonna see the secant and the tangent goes away. Boom, boom. There's an a on the top. It's gonna go away with one of the a's on the bottom there. We still have a lonely a at the bottom here. So we have integral of 1 over a d theta. Well, this is very similar to the very first one, actually the second one as well. This is just going to be 1 over a theta plus your cheese. But once again, we want this in terms of u. So we're going to go ahead and revisit our secant theta. What happens when we take the secant inverse or the arc secant of both sides? Well, that's going to give us that theta is equal to the arc secant of u over a. And now we go ahead and rewrite this as 1 over a arc secant, or secant inverse if you want to think about it like that, of u over a plus your cheese, and that is our answer right there. These are the 3 fundamental integrals that we need to know, and I hope that you enjoyed this. Please subscribe to my YouTube channel, and if you want more integrals like this, a little, something more difficult, let me know, and I'll see you in the next one.